We're Design Team 23 for Chemical Engineering Senior Design. Our team name is Notorious ChE. Our team is comprised of myself, Kylie Kinlow, Anirudh Nambiar, Claire Fisher, and Gavin Schuler. We were tasked with producing ammonia from a natural gas feed. Schuler. This presentation focuses on our process overview, our product, the economic analysis, and our recommendations on how to proceed with this project. Nitline Chemicals has two existing locations. The first is in Philadelphia, Pennsylvania. The second is in Houston, Texas. Houston, Texas has the major benefit of a ship channel from which we can use pipelines to receive our materials. The Gulf of Mexico is concentrated with pipelines like these, as you can see. Our Houston, Texas location is shown here. The raw natural gas is fed to our plant from the ship channel pipelines at the compositions below. As you can see, the natural gas is comprised mostly of methane with some additional components, including small amounts of heavy hydrocarbons, nitrogen, carbon dioxide, and a few hazardous substances, such as hydrogen sulfide and mercury. Ani will cover more on this later. Our plant takes in 32 million standard cubic feet of natural gas a day. The first specification from Nitline Chemical is that we're required to meet a 99.5% pure ammonia product. The second specification is that 90% of the methane from our feed must be converted to ammonia. This means that we have a target production of 97,000 pounds per hour, meaning that we're producing 815 million pounds of ammonia per year. We hit the bullseye on all of our target specifications, including 99.9% pure ammonia product. We're producing 136,000 pounds of ammonia per hour, which means that we're producing 1.2 billion pounds of ammonia per year. This is 41% more than we're required to produce. Now Ani's going to talk about how we produced all of that ammonia.
Phase 4 is ammonia production, and I'm going to talk about each of these phases one by one. So let's start with phase 1. In phase 1, we have feed purification, where we have some impurities, so namely hydrogen sulfide and mercury. Hydrogen sulfide is present at a concentration of 1.5 mole%, and we have 20 parts per million of mercury. So the way we remove these two contaminants is by taking a packed tower, and we remove mercury by absorbing mercury onto activated charcoal. And so the mercury is absorbed onto the activated charcoal and the feed passes through purified. And so we were able to reduce the concentration of mercury from 20 parts per million to 0.1 parts per trillion, which is a significant reduction in the mercury concentration. Next, we used another packed bed. This time it was packed with zinc oxide. And here, hydrogen sulfide reacted with zinc oxide to form zinc sulfide, which is left on the solid, and water. And so in this way, we were able to remove hydrogen sulfide. Next, we go to phase 2. In this phase, the purpose is to produce hydrogen, and the main unit operation in this phase is the steam reformer. And so in this reactor, we basically have many reactions happening. The main reaction is the reaction of methane with water or steam to form carbon monoxide and hydrogen. Since we also have higher molecular weight hydrocarbons, we have other reactions going on which produce more carbon monoxide and hydrogen. Since this is an endothermic process, we need to add a lot of heat to this process, to the reactor. And so we ran this reaction at 900 Celsius and around 26 atm. Next, we used a water gas shift reactor to convert the carbon monoxide that was formed in the steam reformer into more hydrogen. And so in this reaction, carbon monoxide reacts with water to produce carbon dioxide and more hydrogen. And in this reaction, we had around 20,000 pounds of hydrogen coming in, but then after the reactor, we had 27,000 pounds per hour of hydrogen. This leads to 137,000 pounds of ammonia being produced in the downstream process. We ran an alternate process study where we didn't have the water gas shift reactor, and in this case, we could only produce around 103,000 pounds per hour of ammonia, which is a significant reduction in the amount of ammonia produced and therefore revenue. Next, we had some other purification steps. So to remove the water, we used a condenser, which is at a temperature of 96 degrees Celsius, which is below the boiling point of water of 100 Celsius. We also used a pressure swing adsorber unit to purify the hydrogen before it went into the ammonia reactor. And so the the pressure swing adsorber was loaded with a zeolite adsorbent, which basically removed the impurities and produced hydrogen at a purity of 99.999%. Next, we also have heat integration. So, because of heat integration, we were able to save energy, and we ran some alternate process studies, and we found that we could save $5 million of cost by heating up some process feeds using the effluent of our steam reformer, which is at a very high temperature. Next, we have phase 3, which is nitrogen production. And so here, we just took air, we compressed it, and then we put it into a pressure swing adsorber unit, which is loaded with a carbon molecular sieve. And so this removes contaminants such as oxygen and produces very high purity nitrogen at a purity of 99.999%. Next, both the hydrogen and the nitrogen streams were fed into the Haber-Bosch reactor. In this reactor, the reaction that is occurring is a reaction of nitrogen with hydrogen to form ammonia. This is a very well-studied process. It is also an exothermic process. And so if you raise the temperature, the equilibrium shifts towards the reactants. But you want to raise the temperature to achieve a high rate of reaction. And therefore, we chose to run with a compromised temperature of around 345 degrees Celsius and a pressure of 247 atm to maximize the yield of ammonia in a quick time. This is what the process looks like. So we have a staged compressor to basically compress hydrogen and nitrogen in steps so that the temperature doesn't go too high. We then feed the compressed reactants into the Haber-Bosch reactor. We have a 55% single pass conversion of hydrogen. And so we have some unreacted hydrogen and nitrogen. This mixture is then fed into a condenser, which selectively condenses ammonia at a temperature of minus 27 degrees Fahrenheit. The unreacted reactants, which are in the gaseous phase, are then recycled into the reactor to increase the overall conversion. And so through this process, we're able to produce 137,000 pounds of ammonia per hour. Next, Claire will talk about the process safety.
As I mentioned earlier, we are producing a highly pure ammonia product. We're using a PSA unit to separate hydrogen from nitrogen, carbon dioxide, methane, water, and carbon monoxide. This is done at an optimal pressure of 40 bar to get hydrogen to 99.99% purity. We also use a PSA unit for the separation of nitrogen from the other components of air, and this is done at the optimal pressure of 8 bar to get nitrogen to a purity of 99.99%. With highly pure nitrogen and hydrogen streams, we're able to produce an ammonia product of 99.9% purity. The material of construction was analyzed for each unit operation in order to prevent corrosion and other material failures. The main concern when choosing material is the design temperature, since we're running at very high temperatures and pressures in our unit. Carbon steel was appropriate for most vessels, however, it is brittle below negative 20 degrees Fahrenheit and cannot withstand temperatures above 750 degrees Fahrenheit. Because of this, we chose stainless steel 316, as it can operate at higher temperatures as high as 1400 degrees Fahrenheit. There are several highly flammable materials in the plant, so these materials must be handled with extra caution to prevent explosions or fires. Although it will be inherently safer to lower the temperatures and pressures of potentially hazardous streams, this cannot be done. We would not produce any ammonia, as we need to operate at high pressures in order to make our pressure swing adsorption units work as well as we need them to, and also the Haber-Bosch reactor operates at high pressure as well. Therefore, plant safety will be dependent on process controls such as control valves, temperature sensors, and pressure sensors to handle the high temperature and high pressure situations. Proper disposal must be used for the waste streams present in our plant because toxic materials are present in some of the streams. We're removing mercury and hydrogen sulfide from our feed due to their hazardous properties. Mercury must be removed because it's incompatible with ammonia. And hydrogen sulfide must be removed because sulfur deactivates catalysts used in downstream processes. The mercury removal and the zinc sulfide removal will be handled by a waste removal service, as it is a complex process to incorporate into the plant design and it's quite expensive as well. The other waste streams containing carbon monoxide and carbon dioxide, among other components, will be incinerated, scrubbed, and then released to the atmosphere at safe concentration levels. Sensors will be implemented to reduce hazards from gaseous products. We'll have an ammonia sensor in our plant to detect leaks in our vessels containing the gas, and this will help protect employees from inhaling harmful concentrations of the gas. We'll also implement a NOx gas sensor in the nitrogen oxide, just in case nitrogen oxides are produced and released into the plant, and this will help prevent occurrences of combustion. And now Gavin will discuss the economic analysis for our process.
The entire process. Firstly, since we are an established commodity plant, we have a lower discount rate than the industry standard at 9%. An NPV with the discount rate of 9% would yield $285 million over an 18-year period. With a 12% discount rate, we would yield $193 million over an 18-year period. Another measure of our economic profitability is our after-tax rate of return, which is 29.4%, well above the industry standard of about 15%. Lastly, we have the required netback, and that is about 50% of our revenue is eaten up by costs, which is really very good. Now we have our total capital costs of $150 million upfront. You can see by this pie chart that it's a breakdown of all the components. Most of our capital costs consist of compressors and our heat exchangers. Additionally, the reactors eat up some extra capital, with steam reformer and Haber-Bosch being the most notable, as they run at high temperatures and high pressures. So they need to be extra padded and have extra heavy material to accommodate those conditions. Other thing to note, not included on the pie chart, is site development and product storage, and contribute about $50 million to our capital costs. Now we see the operating cost breakdown. Again, our operating costs are about 50% of our revenue. Mostly it comes from the natural gas feedstock, which is unavoidable, and the zinc oxide. The zinc oxide is used in the desulfurizer reactor and can be quite expensive as a reagent. Lastly, we have the utilities, which eat up another 23%. The utilities consist of all the electricity, the cooling water, the heating oil for the boiler, and the refrigerant. Now we come to an alternate process study. What we have here is analyzing the waste stream coming out of the hydrogen separator. This stream mostly consists of CO2 in a 93% mole percent. We can very easily separate the CO2, as seen by this normal boiling point line. The boiling point of CO2 is very far away from any of the other contaminants in the stream, and thus a simple condenser will separate and purify the CO2. Once we get the CO2 condensed and frozen to dry ice, we can then sell it on the open market. You can see from the bottom of the slide that the 150,000 pounds per hour of CO2 we have translates to $40 million a year in extra profit. Here is a sensitivity analysis. As we know, natural gas comes out of the ground, and being so, it's naturally going to have a varying composition and flow rate. You can see here our base case has fixed values for composition, but these can range quite widely. Our process and components will need to be flexible and over-designed to accommodate for this. For instance, if we have extra sulfur contamination, our desulfurizer reactor will have to use extra zinc oxide to decontaminate the extra sulfur. Also, if we have more heavies than usual, that will create extra hydrogen and we'll have to have extra nitrogen inflow. Also, we could have more or less of a flow rate than we currently do, and our reactors should be designed for adaptability. Our final recommendations are thus. The NPV is very positive for this process, and we can get our capital at a cheaper discount rate at 9% because we are a well-established commodity. This project will definitely increase shareholder value even if the NPV at the end of everything is not as high as 300 million, we still have a wide margin, and therefore we should continue to move forward with this analysis and construct the ammonia production plant. And lastly, we have some thank yous. We must, as Team 23, the notorious ChE, say thank you to Joseph Mayer and Aaron Bolin, our mentors. We couldn't have done it without you, and appreciate you waking up or staying up late just to help us. Your advice was invaluable and helped us every step along the way. Next, we must say thank you to Professor McFadden for assembling all the helpful information, compiling and giving such entertaining lectures, and generally being there when we needed something. Lastly, we must say thank you to Joseph's puppies, Dash and Diesel, who actually made 8 a.m.'s much more bearable. That much more bearable.
Why is that on 2 slides? Oh well, we can cut that out. Okay, non-chemical. Why are my slides duplicated? I don't understand how that happened. Okay, just you can skip that, and then we can just cut.
now.
I'll talk about the process overview. That's really bad. Something's wrong in there, and I don't know what it is, which we didn't change on the slide.
I'm sorry, I'm trying. I don't have that right now.
I suck.
So,
Do you want to stop it?
I think you can.
Yeah, let's stop it. Sorry.
Oh, jeez. Earlier, we were producing.
Did I mess up?
Yep. That wasn't me that time.
Do you want me to do it?
Books. Diesel and Dasher. No. Joseph's dogs. Dasher. I'm gonna stop.